In section 11.3, we discuss our first convergence test for series. And it will be specifically the integral test, where we'll use improper integrals to understand convergence of series. So this makes sense, right? So if you think about what a series is, it's an infinite sum. When the argument of the sum, the subscript, runs from 1 to infinity. So if you think about improper integrals from 1 to infinity, they are quite similar. The argument changes in the same range, and so it's natural to expect that there will be some connection. So before we formulate the integral test, we will discuss a motivational example. So consider the series 1 over k squared. Okay, so it starts off like this: 1 plus 1/4 plus 1/9, and so on. For the reason that I just explained, we want to relate series, infinite series, to integrals with infinite domains, the improper integrals. And so to that end, we consider the function f of x that generates this series, right? So if you take f of x to be 1 over x squared, then f of k is exactly a sub k. So if you think of these as a sub k, then the value of function at the positive integer k is exactly a sub k. And so let's look at the graph of this function, right? So in order to relate the series to the integral of this function, we will think of its improper integral as area, right? So in this picture, let me maybe remove some notation here. So in this picture, the black curve here is the graph of 1 over x squared, right? So this here is 1 over x squared. The improper integral from 1 to infinity 1 over x squared, like so, is the area under the graph that lies between the vertical line x equals 1 above the x-axis and under the graph of 1 over x squared. So this area shaded in pink, is the improper integral. On the other hand, how do we show our series in the picture as some area? So what we do is we consider points on the graph which correspond to the values of f at positive integers, right? So this is x equals 1, so this corresponding y value must be f of 1. Right? This must be f of 2, and so on. Okay, so the heights are given by the values of f at positive integers. In other words, the heights of these vertical lines, these dotted lines, are precisely a sub k. So this height is a1, this height is precisely a2, and so on. But we want to think of the terms of this series not as heights, not as linear quantities, but as areas. And so for that, we just think, well, okay, because we have heights equal to the values of the terms from the series, we're going to draw rectangles of width 1, right? So all of these rectangles have width 1. They have heights given by AKs, and therefore they have areas given by AKs. This rectangle has area A1 equal to 1. This has area 1 over 2 squared, and so on. This has area 1 over 3 squared, 1 over 4 squared, etc. Okay, so we have now visualized the series that we have, 1 over k squared, as areas of a bunch of rectangles, all of which are under the graph of 1 over x squared. However, if we think about the integral of 1 over x squared, the integral starts at this line here, right? So it does not include the first rectangle. So all but the first rectangles are under the graph, and therefore their areas are at most area under the graph. So if you look at the rectangles starting from the second one, so if you look at these guys, right, their areas are under the graph, and we get this estimate. So we get the estimate if k starts from 2, right? We exclude the first rectangle, then the total area is at most area under the graph from 1 to infinity. But we do want to include the first rectangle, and so we're going to do it separately. So we're adding the first rectangle on the right hand side, and we're adding it in the left hand side, and this way the inequality is still true. So the sum of this infinite series is the area of all the rectangles under the graph of 1 over x squared, which is bigger by 1 than the area under the graph, like so. But the area under the graph is finite because the integral converges. So we have that the infinite sum of our series is at most 1 plus the integral from 1 to infinity x to the minus 2 dx. We can go ahead and integrate that, and we get 2. So the infinite sum of our series is bounded by 2. Okay, so what does it mean? So let me look back. This implies any partial sum of the series satisfies S sub n is the partial sum. For example, it's the sum from k equals 1 to n, 1 over k squared. It is at most the infinite sum right? So if we take a bigger sum, of course we get a bigger value because all the AKs are positive. But this is at most 2. And so the sequence of partial sums is bounded. That is because if you look at partial sums, they are all adding up positive AKs. So we have that all SNs are positive and they are at most 2. Okay, so it's a bounded sequence if we consider partial sums. But we know that the infinite sum is determined at the limit of partial sums. So we have shown that they are bounded. They're also increasing. So if you look at Sn plus 1 minus Sn, this difference is exactly an plus 1, and it's positive, right? So we can even put the strict inequality sign here. And so we can conclude that from here, Sn plus 1 is bigger than Sn, because every next partial sum includes adding a positive AK to the previous partial sum, so we get a bigger value, obviously. So what's the moral? If you look at the sequence of partial sums, it is increasing and it is bounded, and therefore it is convergent, because we had a theorem to this effect. Remember, I told you that this would be an important theorem when you start talking about series. So the theorem said if you have a monotonic sequence which is bounded, it must be convergent, right? Because it can only go one direction up or down, and it cannot go very far because it's bounded. So therefore it must be convergent. It cannot oscillate, because that would mean it breaks monotonicity. It cannot go to infinity, because that would break boundedness. So it must converge. And we obtained that the sequence of partial sums in this case is convergent. So hooray, we win, because it means that the infinite series is convergent. We don't know where it is convergent. Not to 2 though. It will be important that the integral test, just like all the other convergence tests, does not tell you the sum of a series. It just tells you if a series is convergent or not. And in this case, that's exactly what happens. We only know that this series is convergent. We don't know what's its sum. So that's the first application of integral test to determine convergence of a series. Next, we will discuss another example in which we will show that a series is divergent, again using improper integrals. And after that, we will summarize these two examples into the formulation of the integral test. And then we will talk about some more examples. So that's our plan for this section.